In this question, we're given that a relation is defined from real numbers to real numbers, and A is related to B if and only if A cube is less than B square. So if A cube is less than B square, then A and B are related. So you're asked to check whether it is reflexive, symmetric, and transitive. So by the look of the relation, it doesn't look like a standard reflexive, symmetric, and transitive relation. So what I try to do is, I try to see if there are some counter examples where I can disprove this relation as reflexive, symmetric, and transitive. So first, reflexivity. So if relation is reflexive, every element A has to be related to itself. A comma A should always belong to R. I just want to check what is the condition which ensures that A cube and A are always related. So if A cube and A are related, A and A are related to themselves, so A cube should be less than A square. So is it always true that A cube is less than A square? No, right? So if you take a counter example, 2 cube less than 2 square is wrong, because 2 cube is 8, 2 square is 4. 8 is less than 4 is wrong, and so 2 comma 2 does not belong to the relation. So you got a counter example, hence this relation is not reflexive. So to disprove that a relation is reflexive, you can just get a counter example and you're done. And the second, symmetry. So let us see whether this relation is symmetric or not. So symmetry says that if A is related to B, B has to be related to A. So does this hold good here? So let us try to find some counter examples. So 2 cube is less than 2 cube is 8 is less than 3 square. 2 cube is 8 is less than 9. That means 2 comma 3 belongs to the relation R. So does 3 comma 2 belong to R? So if 3 comma 2 has to belong to R, then 3 cube should be less than 2 square. 27 is less than 4 is wrong. Hence 2 3 belongs to R, but 3 comma 2 does not belong to R. Hence this is not symmetric. So one counter example is sufficient. Third, transitivity. So here also let us try to get some counter examples. So finding a counter example is not always easy. So you have to think in different ways. So let us take A as 0.5. So let us start with that. A as 0.5. Now I'm going to take an ordered pair where the first element is 0.5. So 0.5 whole cube should be less than B square. So 0.5 whole cube is 0.125. So I'll take B as 0.4. If I take B as 0.4, B square is 0.16. So 0.125 is less than 0.16, which is true. That means 0.5 comma 0.4 belongs to R. Sorry, the relation is S. So relay belongs to S. Now I want an ordered pair of the form 0.4 comma something. Now 0.4 whole cube is less than something square again. So what is 0.4 whole cube? 0.4 whole cube is 4 cube is 64. So 0.064. So 0.064 is less than, I want to get some number here. So can I get a 0.1, 0.2, so 0.25 whole square is 0.0625. So 0625 is less than 0.64. 0.26 whole square. I'm taking very close numbers so that I want to get a counterexample. 0.26 whole square is 0.0676. 0.064 is less than 0.26 whole square. 0.26 whole square is 0.0676. 0.064 is less than that. It means 0.4 comma 0.26 also belongs to this relation. Now let us check if these two 0.5 comma 0.26 belong to this relation. Now 0.5 whole cube is less than 0.26 whole square. So 0.5 whole cube should be less than 0.26 whole square. So what is 0.5 whole cube? 0.125. And 0.26 whole square is 0.0676. So is this true? 0.125 is less than 0.0676 is wrong, because this is greater. Hence 0.5, 0.4 belongs to S. 0.4, 0.26 also belongs to S. But 0.5 comma 0.26 does not belong to S. Hence the relation is not transitive. So I got the counter examples to disprove reflexivity, symmetry as well as transitivity. So this is a very important thing to understand. So if you feel that relation is not reflexive, we just need to find a counter example.